Okay, everybody, welcome back. Happy Friday to you. Today's a big day because we're going to do the probably longest mechanism that you'll ever do in this class. Though, if you break it up into conceptual chunks, it's actually not really that much that's new. It's called the Robinson annulation, which we'll get to. But before we do that, we need to finish up on the Claisen reaction. Hopefully you took a look and could see how we could get from this sort of 1,6-diester to the 5-membered ring-containing product. The intermediates in this process are all shown here. The arrows to get from here to here, notice mechanisms aren't as hard as you think they are, because if you have the starting material and the next intermediate, you know what has to change, and so figuring out what the arrows were isn't that big of a deal. For example, starting material enolate. I got to deprotonate at the alpha carbon, right? And you know how to do proton transfer. So, and in the same way, if you have the arrows are the instructions for making the next product. For example, here I have an enolate and a tetrahedral intermediate. We were thinking backwards, but now I'm imagining how I would do this in the forward direction. Well, alpha carbon enolate attacks the beta carbon, electrons kick up. Those are the two arrows that get me to my tetrahedral intermediate, and so on. Leaving group leaves, electrons kick down from the oxygen, and the leaving group leaves. All right. So that's the Claisen reaction. Go ahead.
If you put a methyl group on number 4 in that ring, would we be able to tell which one it would selectively attack?
Okay, so right, good question. So if you want to suddenly make carbons 1 and 6 not equivalent by putting a methyl group on carbon 4, would you expect to get one enolate over the other, and would you get a mixture of products? Yeah, you would get a mixture of products. I suppose somebody out there is thinking, well, what if I made one of the two alpha carbons more substituted? Remember, it all has to do with the stability of the ring product that's formed. So I'm not really sure what you would expect to get there. Would you expect to deprotonate here and attack this carbon, or deprotonate there and attack that carbon? I'm not sure. I know that someone else out there is thinking, well, if you're not sure, are you going to give us that on an exam? No. Okay. Your text has a section which you should read and practice some problems in about the so-called crossed Claisen reaction. We talked about the problems associated with the cross-aldol reaction. Same sort of things apply to the cross-Claisen reaction. You can get a mixture of products because if you bring two different esters together, you're never sure who's going to be the enolate and who's going to be the electrophile. The workarounds for the crossed Claisen reaction are similar. For example, I'll show you one where you use as electrophile an ester that lacks alpha protons. So you can't form an enolate from here, which means that when you do the Claisen reaction, again, you would choose a base that matches the identity of the group on your ester, so that the background undesired nucleophilic acyl substitution reaction you can't tell. Under these conditions, you could only make this enolate, and then you would expect that enolate to attack this carbonyl carbon, and you should get the crossed product, which for a Claisen reaction is this beta keto ester. Again, the purple is the enolate, the orange is the molecule that was the electrophile, There's where the orange atoms end up. There's where the purple atoms end up. But you would still worry about the potential for self-Claisen reactivity of the purple molecule, because there's nothing really built in here to prevent the purple molecule from reacting with, the purple enolate from reacting with non-enolate starting material to get the self-Claisen product. Okay, so read that about sort of cross-Claisen workarounds to get an idea, but there's not a whole lot new there relative to what we talked about for the cross-aldol reaction. Let's see. Another option, which sort of another example of this kind of thing, the cross-Claisen reaction, is, and this is perhaps a subset of the use as an electrophile a molecule with no alpha protons. It turns out if you're careful, you can do a Claisen reaction between this ester in purple and this strange orange almost ester. This is chloroethylformate. You don't need to know that. It's not exactly a carboxylic acid derivative. Carboxylic acid derivatives have 3 bonds to heteroatoms. This one's got 4. So this is actually at a higher oxidation state than a carboxylic acid. It has dual character. It's sort of an ester, and it's sort of an acid chloride. And so you can predict its reactivity. A carbonyl carbon with 2 leaving groups should be able to do nucleophilic acyl substitution. You can have the alpha carbon attack the carbonyl carbon as expected. This would give you a tetrahedral intermediate. The bond formed is now in red. Here's the negatively charged carbon. But now we've got leaving groups all over the place, and it turns out chloro is the better leaving group. So electrons can kick off the chloro, and that allows us to make this beta diester. So you'll see some examples in your text of using this reagent, and it's a strange one that you haven't seen before, ethyl chloroformate. You don't need to know that name, but I might use it. But this is a way to use the Claisen reaction to make a molecule that you've seen before. That's a molecule from chapter 17. We used that in the malonic ester synthesis to do enolate alkylation. And of course, you know, if you do, we've also talked or rather showed you last time how to use the same basic Claisen reaction to make this acetoacetic ester from simple starting material. Why am I bothering to review this? Because in this class we love pesky synthesis questions, and now we can repeat some synthesis questions that you had from chapter 17, but push them backwards even further to even simpler allowed starting materials. For example, straight out of your nightmares to this class is this desired product, but you only get to use this and this and any alkyl halide you want. Now, if you have not practiced and worked through some of this, you are not going to see any connection whatsoever between these allowed starting materials and this product. Okay? No chance, right? So you got to practice this. And this builds on practice that you've done in chapter 17. So for example, in chapter 17, you learned that if you've got an alpha-alpha dialkylated carboxylic acid as a product, I'm trying to teach you to look at structural patterns in products to help clue you into synthesis. This is an alpha-alpha dialkylated carboxylic acid. How can I tell that? Well, it's a carboxylic acid. If you can't recognize the carboxylic acid, there's not a lot I can do for you at this stage, but please do come talk to me and we can work through it. That's a carboxylic acid. This is the alpha carbon, and there are 2 alkyl groups on it. So when I see that from chapter 17, the big jump backwards from a retrosynthetic point of view is the malonic ester synthesis. I'm not going to review that today. We reviewed that a couple of times in a previous lecture. If that's still a weak point, come talk to me in my office hours, go look at the lecture video, review the portions of the text. But hopefully with a little bit of practice, you'll be able to see how you could have gotten this product from malonic ester as a starting material and a 5-carbon alkyl halide. I won't draw that mechanism. I'll summarize it briefly. You'd use a base, sodium ethoxide, to remove the especially acidic alpha proton here. You'd do one alkylation reaction to get a monoalkylated diester product. Then you'd introduce a second molecule of sodium ethoxide to remove the second proton, and the new enolate would then react with the other alkyl halide at the end of that chain to make your 6-membered ring. Then you would use acidic conditions and heat to do ester hydrolysis, decarboxylation, and tautomerization, which gives you this carboxylic acid. Okay? So I'll just, again, warn you, if that doesn't sound familiar to you, you've got some work that you need to do in reviewing chapter 17. Okay, so in terms of our synthetic plan, we can check off this alkyl halide, which is allowed, but I wasn't allowed to use malonic ester, so how do I get it? Can I get it from these 2 starting materials? The answer is yes, I just showed you how. So that's the sort of crossed Claisen reaction between this ester. We might want something to call this ester. It's actually called ethyl acetate, and then ethyl chloroformate to give you the malonic ester. All right, so just practice that because it's kind of a cool way to build up a lot of complexity from very simple starting materials. I probably will not be able to resist doing something like this on the exam. I don't normally disclose those things in advance, but I'm feeling talkative today, so. Okay, questions about that? Yeah.
The melodic ester, and it turns into the carboxylic acid. What's, I guess, how does that work? 'Cause I understand the Br is going to attach to that conjoining carbon, but just how to get that final product.
So are you good with the enolate alkylation portion?
Yeah.
The successive. So you should be able to see how you can get from here. I'm abbreviating the ester groups to here. Okay, so that's the enolate alkylation. Remember, and that will occur in sort of 2 successive steps. Then you're going to use H3O plus and heat to do, and go back to the second, was it the second lecture on chapter 13 or the first? I think it's the second. Ester hydrolysis, decarboxylation. and tautomerization. So we've done that mechanism before, and that's probably worth some review. Okay, what else? Yeah.
Why would we need any alkyl halide on that product set?
I was just over here, of course, no, the alkyl halide is not a portion of the Claisen reaction. I was just telling you what was allowed as starting materials. Yeah. All right. Others? Yeah.
What's the benefit of using the weird chloro product as compared to the diethyl carbonate? Are they just the same thing at this point, or?
Oh, the weird chloro product, ethyl chloroformate. Also, let's see, you could swap out. Yeah, you're pointing out something in the text. You are able to swap out ethyl chloroformate for this other starting material, which is called diethyl carbonate. Carbonates, I think, are a little bit less reactive than the chloroformates are. And that just reflects the fact that chloro is a better leaving group. Probably this reagent's a little bit more stable though, and more shelf stable, so it may be more convenient to use. Your text shows both of these as options. The mechanism is the same for both of them. The only difference here would be OET minus would be the leaving group. That's okay because you got a negatively charged oxygen. You can feel free to use them interchangeably. Yeah. All right. I want to talk now about nature's use of the Claisen reaction. We talked about how nature uses the aldol reaction. So, and that was doing a retroaldol reaction in the glycolysis pathway in metabolism. The Claisen reaction in biochemistry, the best example of this is in fatty acid synthesis. So this is how you synthesize a long chain carboxylic acid that you then incorporate via an ester bond into glycerol to make a triglyceride or a fat or an oil. Okay, so nature for its Claisen reactions uses thioesters. You've learned about thioesters. They're great in nucleophilic acyl substitution reactions. And frankly, the Claisen reaction is an example of a nucleophilic acyl substitution. It's just you're using an enolate as the nucleophile. So in fatty acid synthesis, you have a sulfur, and then that sulfur is connected to something called the acyl carrier protein. The connection between the sulfur and the carrier protein is known, and we could draw it, but it's not really that relevant to the discussion of what's going on, so we just won't worry about it. Okay, so here you've got, in this case, just a 2-carbon carboxylic acid now as a thioester with a sulfur from a large carrier protein. Then the other reactive partner is something that's called malonyl-CoA. I talked about this a couple of days ago when we talked about decarboxylation. And I mentioned that biology sometimes uses beta carbonyl acids as masked enolates. What I'm drawing for you now is malonyl-CoA, or we'll just call it a malonyl thioester, because we're just going to put an R group there and not worry about what it is. Notice that this malonyl thioester is a beta keto or a beta carbonyl acid. And you know that these things can decarboxylate. You've hopefully learned to think about you've hopefully learned why they can decarboxylate, and the answer is that if the oxygen takes its electrons and those electrons kick down and the leaving group here is the enolate leaves, it will leave as a resonance stabilized negative charge, okay? So I'll draw stepwise what a lot of people will probably draw in a single step, but I do want to show you the formation of the enolate. Decarboxylation, and sometimes in biochemistry they'll indicate that this happens by showing you an arrow like this with CO2. I'll show you in purple where the CO2 comes off. It's that carbon and those two oxygens. Decarboxylation leads to this enolate, which is resonance stabilized. I've shown you one of the two resonance structures. The other would have a pi bond between alpha carbon and carbonyl carbon, and then, and then a negative charge on the oxygen. We'll have this alpha carbon attack the carbonyl carbon of the ester. That's the Claisen step. That's going to make a bond between the alpha carbon of my enolate, which I'm labeling in green, and then the carbonyl carbon of my thioester attached to the acyl carrier protein, methyl group, and then I'm just going to abbreviate acyl carrier protein with ACP. Then these electrons on the oxygen kick down and the thiolate leaving group leaves, and the product of that reaction is this beta keto thioester. And I'll highlight the subunits that we've sort of linked together. These carbons, two carbons, and the oxygen come from the acetyl thioester that was on the acyl carrier protein. And these two carbons and the oxygen come from the malonyl thioester. Okay? And it turns out that the fatty acid synthase that does this reaction is a multi-subunit enzyme complex. And the thioester that is attached to the acyl carrier protein basically moves this molecule around to various subunits like a crane, and other things happen. For example, ultimately, if we want to make a fatty acid, we've got to get rid of the beta keto group, and so that we just have the alkyl thioester. And there are other subunits in the fatty acid synthase complex that do reduction of the ketone, elimination to give an alkene, and then reduction of the alkene to give the alkane. But it all starts with this reaction between the malonyl thioester and actually once you get to this point, the enzyme takes this molecule and puts it right back here, and then you go through another cycle and stick on another 2-carbon subunit. And this is why all of the fatty acids that your body makes have even numbers of carbons, because that's how you chunk them on through this enolate reaction. Okay, questions about that? Do you want us to have the structure of the acyl carrier protein memorized? Well, naturally, since we didn't talk about it at all, you should definitely, no, of course not. You should understand the mechanistic steps. You should understand how this is an example of a Claisen reaction. All right, so we got 2 more reactions to do in chapter 18. One of them is is a variation on a reaction that you've seen before. It's called conjugate addition we saw this before, or alternatively, it's called 1,4 addition. You saw this before in chapter, whatever it was, 13 on cuprate chemistry. Cuprates can attack alpha beta unsaturated carbonyl compounds at the beta carbon. When the enolate, we're going to, in this case, use an enolate as a nucleophile. The reaction is called the Michael reaction, or sometimes called Michael addition. Though that term, Michael addition, Michael reaction, has gotten to be even broader than just enolates. Basically, for a lot of people, if you show a nucleophile attacking the beta carbon of an alpha beta unsaturated carbonyl compound, they're going to say, oh, that's a Michael reaction. So we'll use conjugate addition, 1,4 addition, Michael addition, or Michael reaction somewhat interchangeably. As I said before, you've seen this in chapter 13 when we had an alpha beta unsaturated carbonyl compound, and then we used, say, a cuprate reagent. I don't know which one to choose, so we'll keep it simple. Here's a cuprate reagent. The cuprate reagent delivers the organometallic sort of carbanion equivalent to the beta carbon. We can either push arrows by moving the bond between beta and alpha, double bond between beta and alpha carbons onto the alpha carbon, or alternatively, we can push arrows to get the other resonance structure of the resulting enolate. Here is the new bond that you make in red. And here is the enolate. I've drawn one of the two resonance structures of the enolate. Any of those resonance structures are okay. I'm going to continue to label what used to be the carbonyl carbon, and then we have delivered this nucleophile, except we gained a carbon strangely, didn't we? Somebody was going to say that. So the idea here is that we have delivered what used to be a nucleophile, and it's now forming a bond to the beta carbon. And then after the Michael addition reaction, we protonate. In the chapter on cuprates, we said we probably protonate on the carbonyl oxygen first to get the enol, which eventually tautomerizes to its more stable keto form. So the product of conjugate addition, as I said, has a nucleophile attached to the beta carbon, and you're basically trading this carbon-carbon pi bond for a new carbon-carbon sigma bond and another carbon-hydrogen sigma bond. If you're thinking about what's present in the product that wasn't in the starting material. So as we do the Michael reaction with an enolate as our nucleophile, pay attention to the kind of products that we get, and you're going to see this same pattern. The enolate's going to end up attached to the beta carbon. So let me give you an example of using an enolate as a nucleophile in a Michael reaction. So we'll use the same, we're going to use the same alpha beta unsaturated, well, maybe not exactly the same. Let's use an aldehyde as our electrophile. In a Michael reaction, your electrophile is always an alpha beta unsaturated carbonyl compound. Okay? And it's going to be electrophilic mostly at the beta carbon. Then let's use as a nucleophile this beta diketone. I won't show you the deprotonation step. The base you use for the Michael reaction doesn't matter. It can be a cheap base. In this case, you would remove a proton from the beta diketone as your first step to make the enolate. And then, having made the enolate, everything we do from this point on is going to be the same as for the cuprate conjugate addition. The only thing is that our nucleophile is now a little bit larger, but the atom that's nucleophilic is the alpha carbon of the enolate. So, electrons attack the carbonyl carbon. You can draw that process in one of a couple of ways. The electrons over here between the alpha and beta carbons can either go onto the alpha carbon as a negative charge to give you the enolate, or you can draw the other set of arrows leading to the other resonance structure like I did above. The product of that reaction is this. Negative charge on the alpha carbon. Here's the beta carbon. Here is the new bond I made between the alpha carbon of my nucleophile and the beta carbon of my electrophile. I should have chose different colors, but oh well. Fine, I'll change it in line. This is now in pink, the alpha carbon of my enolate. And then that alpha carbon was attached to two ketones. All right. And then to get to my product, I simply protonate on the alpha carbon. Probably in reality what happens is I protonate on the oxygen first to get an enol, and then I tautomerize to get the more stable keto form. So this would be my product. Again, labeling all the carbons. This portion in blue of my molecule came from my alpha beta unsaturated carbonyl compound. This portion in pink was my enolate. And that is the product of a Michael addition reaction. Okay, questions about that mechanism? Yeah? Which steps are reversible and which are not? I know that retro-Michael reactions are possible, but I don't think your text talks about them. Let me just check on that. But I think that's true. Yeah. Yeah, the text doesn't really tell you that. It just shows forward arrows, so I'm just following that. Good, yeah?
Are we assuming that the alpha proton, alpha beta unsaturated carbon compound is not acidic enough to be competing with
Right.
that ketone?
Right. So if you have both of these starting materials in, the question is in the same pot, and then you add a base. The question is, do you have to be worried about the acidity of this alpha proton? And the answer is no, not in alpha beta unsaturated carbonyl compounds. It turns out that the carbonyl here is conjugated to the double bond. That holds this carbon hydrogen bond orthogonal or perpendicular to the pi system. of the carbonyl. What that means is if you deprotonated it, the electrons there would be held in an sp2 orbital perpendicular to the double bond and not actually conjugated with it. What makes alpha protons acidic in the first place is that their resulting conjugate bases, the enolates or resonance stabilized. That's not going to be true here for the alpha beta unsaturated carbonyl compound. The other thing is just that the pKa of the beta diketone, and I think in many examples in your text, the Michael reaction uses a beta dicarbonyl compound as a nucleophile. That's just the most acidic proton you got here. Good, other questions? So let's make it worse with a few Greek letters and pattern recognition. As you've learned to recognize products of previous reactions, that should help you grow into doing synthesis questions more effectively. For example, we just barely talked about beta ketoesters as a pattern for products of Claisen reactions. Let's talk about the structural pattern for a Michael product. And here, you want to look for a distance between the carbonyls in the Michael product, because Michael products are going to be what I will call dicarbonyl compounds. Because you have to have in your starting material a carbonyl from your alpha beta unsaturated molecule, and you have to have at least one carbonyl from your enolate. And those two carbonyls are still present in the product, and they are 1, 2, 3, 4. Sorry, there's a color clash there. Pink on orange, 4 and 5. So the Michael product is always a 1,5 dicarbonyl. And so when you see a 1,5 dicarbonyl, you can start to think, okay, I could have made that via a Michael addition reaction. Okay. So let's see. At this point, we can begin to put it all together by showing you a series of reactions that combines the Michael reaction with, actually first I want to do a practice problem. So this one happens to be 18.26 A in your text. I don't know if that's assigned in the study guide or problem set or not, but you can check it off if you work through it with me in class here. So the question is, what starting materials are needed to prepare this molecule via the Michael reaction? So first we want to verify that we can even do it. So let's check the spacing between carbonyls. 1, 2, 3. Okay, probably not that connection via the Michael reaction. 1, 2, 3, 4, and 5. There it is. So now that we've seen that, we need to decide which portion of our molecule was the alpha beta unsaturated carbonyl compound and which portion was the enolate. And there's going to be two different ways we could do this, one of which makes better sense than the other. Okay? Going back to our Michael product, we've said that the two carbonyls are 5 carbons apart. Relative to the carbonyl carbon of my alpha beta unsaturated portion of the molecule, the blue portion, the alpha carbon of my pink enolate is gamma relative to the blue carbonyl compound. I think I just made that terrible. Let me try that again. Here's our Michael product. The pink portion was our enolate, and the blue portion was our electrophile, our alpha beta unsaturated carbonyl compound. And I want you to notice that in the Michael product, the pink alpha carbon from my enolate, there, I feel better about that now. The pink alpha carbon of my enolate ends up gamma to the blue carbonyl carbon. No? Yes? Ish? Still no? Okay. Just a way of saying that the atom, the alpha carbon on my enolate ends up bonded to the beta carbon of my alpha beta unsaturated carbonyl compound. I'm only doing this so that we can come back here and look at this product and try to decide which portion was blue, the electrophile, and which portion was the enolate. If I say this portion here was the electrophile, and this gamma carbon is the same as the pink alpha carbon, that would mean that this portion is my alpha beta unsaturated carbonyl compound, and this is my enolate, right? Now there's an alternative. Another potential way I can be thinking backwards and disconnecting this molecule is like this. Let's let this be the carbonyl carbon, this be the alpha carbon, this be beta, this is gamma, or in other words, the alpha carbon of my pink enolate. And then I'm going to use a red squiggly line to indicate the bond that we would have made in the Michael reaction. You see those two distinct possibilities? One of them's better than the other. Any idea why? Well, the one on top is clearly better because I did it first, but why is it better? Go ahead.
It has to do with that acidic proton, which is just higher or lower in pKa.
Right, so if you're thinking about what the, if we draw in blue what the alpha beta unsaturated carbonyl compound would have been, that's it. And then the enolate in pink, let's draw that, and you're noticing that that enolate is the conjugate base of a beta dicarbonyl compound, which should have an acidic proton that would be easy to remove and which we could make in basically 100% yield, right? The pKa of that proton should be around 13. If in contrast we tried to do things this way, our enolate would be like this, and that's the conjugate base of just a regular ketone whose pKa is around 20. Our alpha beta unsaturated carbonyl compound would have looked like this, and there's not necessarily anything wrong with this as an alpha beta unsaturated carbonyl compound, only it's a little bit more complicated. This is a fairly simple molecule, and this is an especially acidic alpha proton, meaning you could make this enolate without having to worry about the potential for a self-aldol reaction interfering, and I would worry about the potential for this thing to react in a self-aldol way. Okay, so if you got a choice when thinking backwards retrosynthetically, choose to use as enolate the most acidic enolate that you can, given the situation. Follow-up questions on that? Not sure that was helpful. Yeah? I think if you look at the answer from the text, the only answer is this one. I walked through this because some of you were likely going to do this problem, come up with this answer, and then wonder why is it wrong. Yeah, and the answer is it's better to do it this way because you use enolate that's easier to make. Okay, what else? So maybe we need to highlight this point. We'll put unnecessarily complicated. Okay. So with that in place, your text has a section 18.10 on something called the Robinson annulation. And this is historically an important reaction. It makes a 6-membered ring, and it's been used to make a lot of interesting natural products. However, I sort of worry that the presentation in the text is needlessly complicated because this isn't really a new thing. It's not a new reaction. It's an application or a connection of 2 different reactions to get a more complicated product. It's named after the person that discovered it. And then annulation means ring forming. From the same, I think, either Latin root for a cycle or a ring. Spanish speakers, a ring is a what? Anillo, right? Same word. An annual, the year keeps coming around. So annulation is making a ring, making a 6-membered ring. I know that making a ring turns on the fiery SpongeBobs. So you're going to need, if you weren't here, if you don't understand that reference, you got to go back to the lecture from a couple days ago. I'll leave it to you to search through the whole YouTube video to see if you can find that Easter egg. So the Robinson annulation is only painful because it's got multiple steps, but in reality, it is just a Michael addition of an enolate to an alpha beta unsaturated carbonyl compound, followed by an intramolecular aldol reaction to make, and the product is a 6-membered ring. It's always, the product is always a cyclohexenone, which just that basic structure, cyclohexenone, that's what it looks like. So we'll go through this in the forward direction, and then we'll think about it in a retrosynthetic direction. But why don't we take a break before we jump into the breach? Let's take 5, and then we'll dive right in.